Okay, I will start with the introduction because we are a bit late and it's a long one, Jeff. So it's hard to introduce someone like Jeff Dean, who has such a long career with so many important contributions to the field of computing. It's also good to have good friends that write well, so I thank Gabi, one of our organizers, for her contributions to this speech. To prepare for this, we decided to use no less than Google. So when Googling for Jeff Dean, you can find, for example, the article, The Friendship That Made Google Huge, by The New Yorker, about Jeff and Sanjay's early collaborations at Google. We also found Quora questions wondering, what is the story of Jeff Dean? How did he become so good at what he does? And simply, how to become Jeff Dean? You also have some Jeff Dean facts, including once in early 2002, when the index servers went down, Jeff Dean answered use queries manually for 2 hours. Feel free to ask him about this at dinner tonight. He will be there. So Jeff joined Google in 1999 and was amongst the first employees. Throughout his career, he has proven himself time and again one of the company's most impactful engineer leaders. He co-designed and co-implemented systems such as MapReduce, BigTable, Spanner, several generations of Google query serving and advertising systems, and most recently, the open source TensorFlow platform for machine learning. He currently serves as the Senior VP of Google AI and Health. But most importantly, I want to mention Jeff's dedication to social good, and in particular for pushing inclusion in machine learning. Jeff's value of diversity goes back many years. Growing up, he lived in a few countries, including Somalia, Uganda, and the Philippines. Jeff has been a big supporter of initiatives such as Khipu and deep learning in Daba. And Jeff was one of the first to agree to speak at Khipu. And it was thanks to his support that we were really able to get Khipu off the ground, convincing many other speakers and sponsors that this event would in fact be happening and that they should sign on too. So thank you, Jeff, from all of us, and we are looking forward to your closing talk at Khipu 2019.
Thank you. Wow.
Thank you.
Thank you for that really wonderful introduction. I think, I've been super impressed with the organization of the conference and the vitality of all the attendees, and the other speakers have been fantastic. And it's just a pleasure to be here. I think it's really important for events like this to happen because they bring people together that wouldn't otherwise necessarily get a chance to come together and to share ideas and experience and research directions they're excited about, to learn from each other. So, thank you. Okay, so I'm going to talk to you today about some applied work in using machine learning to do many different things. And it's the work of many, many people at Google. So we're all here because there's this incredible excitement in the field of machine learning. And there's just this tremendous surge of interest from both the sort of basic algorithmic level, how can we create better algorithms that can do more things that will enable us to then apply things to problems we can't do today, but also to the application of machine learning to many different fields of science, engineering, education. We had a great panel on AI for social good, and we heard about lots of great applications that the other panelists were speaking about. I learned a ton in that. And so there's this flood of interest in growth of machine learning papers is now growing at faster than the Moore's Law exponential rate of doubling every 2 years, which is like pretty phenomenal. Unfortunately, Moore's Law is now sort of kind of dead for improving general purpose computer performance. So we've replaced like the great growth in computing performance we've gotten used to with this growth in sort of ideas and uses of machine learning. And we'll see, I think they're both important. So, and you've heard about many things that neural nets can do, like deep learning can do. So being able to take an image and classify it and tell you which of 1,000 or 10,000 or even 50,000 categories is in an image is pretty important. Being able to take audio and learn completely from examples of audio and what was said, a complete end-to-end learned speech recognition system is super, super important. That is got very low word error rates. So it actually makes speech recognition much more usable, even in noisy environments and in many different languages. Translation systems that are able to take in text, one word or a few characters at a time, and learn to emit the corresponding sentence in another language, purely in an end-to-end learned manner. We replaced the guts of the Google Translate system, which for about 10 years had been operating with a much more complex statistical-based machine translation system that was about, many separate subsystems and models of French and English and how they align and all these other kinds of things. It's about 500,000 lines of code. And, about 3 years ago, I guess, we replaced it with a completely learned end-to-end machine learned model that you could express in about 500 lines of TensorFlow code. And it was the biggest quality improvement that system had ever seen. And it's improved quite a lot since then. But I think this is really, really important because now all of a sudden we make translation much more usable. And you can sort of combine modalities in a really interesting way. Actually, Oriol and others worked on this really interesting kind of idea of how can you sort of, instead of, if you imagine a sequence-to-sequence model for text-to-text, if you rip off the first part and instead make the encoder be a convolutional neural network, then all of a sudden you can train a neural net to take in pixels and generate a caption based on training data that is like images and what you might write as a caption. And then you can caption any old image you've ever seen. This is one of my vacation photos I particularly like. And just to give you the sense of progress and why this is all sweeping the world so much, in 2011, the error rate for the winning entrant in the ImageNet contest was 26% error. That was, and no one used a deep learning model. Then in 2012, Alex Krzyzewski, and Ilya Sutskever and Jeffrey Hinton submitted an entry that used a deep neural net for the 2012 contest and showed dramatic reductions in the error rate, down to about 16%. And we know this is a pretty hard task because Andrei Karpathy, actually, who helped administer the contest when he was a grad student at Stanford, sort of sat himself down and did the kind of human-based machine learning protocol where he would study ImageNet training images and try to predict what the category was. And then he kind of set them all aside after 100 hours, and then he said, okay, now I'm ready to test. And he got 5% error. Another lab mate that he tried to convince to do this same rigorous training didn't participate as much. And they did 10 hours of training for themselves, and they got about 12% error. So this is a pretty hard task. And in 2016, the winning entrant got 3% error. And that has since been driven down, I think, to about 1.8% just this week, actually, last week. So pretty cool. Basically, computers have gone from not being able to see to now they can see, right? And that's partly why we're all here is this has dramatic implications for lots of things and all the other kinds of modalities we can learn end-to-end manners. The rest of the talk, or a lot of the rest of the talk, I'm going to structure around what does this all mean for broader sets of problems that we're working on as society. So in 2008, the US National Academy of Engineering convened a bunch of different experts from many different fields and said, what are a bunch of interesting problems we should be thinking about for the next 100-ish years? And they came up with this list of 14 kind of topics. And I think it's a pretty good list. It's sort of tackling a lot of major problems that we see across society today. It's dealing with kind of how are we going to make the planet not heat up quite so quickly? How can we better educate everyone in the world? How can we make sure that people are healthy? So if we truly solved all these problems, it would be pretty amazing. And at Google, we have work going on all the things listed in red. And I'm going to focus a lot of the rest of the talk on the ones in boldface. So, OK, there's our guide map. Let's start with restore and improve urban infrastructure. So we're actually kind of making pretty rapid progress towards a pretty amazing thing, which is going to be an autonomous vehicle that is actually, widespread deployment of autonomous vehicles. So a lot of the reason this is now happening, even though it's been a dream for many, many years, is that we now have sort of deep learning-based methods that can integrate the many different kinds of sensor information on these cars. So they have like spinning LiDARs on the top that give them kind of some 3D depth information. They have cameras everywhere, basically. And they have like radar in the bumper and the back bumper. And you basically need to integrate all this stuff into a view of the world around you so that you can understand what objects exist around you, ideally so that you can integrate it into a sort of predictive model of where things going to be a second and a half from now. And so that you can also read all the traffic signs. Like you have to obey all the rules of the road, and they're pretty complicated. Don't park here on Tuesdays because of snowplows or whatever, right? Maybe that's lost in the Latin American audience. But there are many, many things you need to do as a autonomous vehicle that are pretty hard. And then you want to be able to have that view of the world and then take safe action in the world, to get you from A to B, which is your ultimate goal. And I think this is like a pretty amazing thing, and it's not like some distant, far-off thing. The Waymo, which is Alphabet is Google's overall corporate structure, and Waymo is our self-driving car subsidiary. Google Research often collaborates with other people in other parts of Alphabet, including Waymo. And Waymo has been making great progress. And so for the last year or so, they've been running tests in Phoenix, Arizona, where they basically normally they have a safety driver in the front seat to take over immediately if something looks like it's going badly. But in Phoenix, Arizona, for the last year, they've been running trials with real passengers in the back seat and no safety drivers in the front seat. So this is like not super far off, right? Now, Phoenix, for those of you who don't know your American geography or cultural aspects, it's a bit of an easier environment for self-driving vehicles for many reasons. So first, it's a pretty warm, nice climate. It never rains. The streets are pretty wide and kind of rectangular, not very complicated like downtown San Francisco or Manhattan or something. The other drivers, often people retire to Arizona, so the other drivers are not necessarily as speedy as other places. But that sometimes makes it more challenging too, I guess. Yeah, I mean, but it's sort of happening in Arizona. It's going to happen in many places. And it's due to the fact that we now can build these perceptual models of the world, integrate all that information, and do pretty amazing things. I think this is going to have a big dramatic effect on robotics as well. Like Chelsea's talk, it was a great illustration of all the things that are now possible from much more end-to-end reinforcement learning-based work in robotics, which is kind of at odds with what has been done for the past 20 years there, which is sort of like very, very hand-coded control algorithms to operate in a very clean, controlled environment. So there are a lot of robots in the world, but most of them are on sort of clean factory assembly line kind of environments. There aren't robots typically running around the world like this, where there's like backpacks to trip on and all kinds of unpredictable things. But the promise of deep learning and reinforcement learning is that we can potentially make robots that can operate in the real world like that. And so I think one thing you would want a robot to be able to do is to pick up an object it's never seen before. And so in 2015, the success rate for a particular benchmark of picking up new unseen objects was about 65%. So we set up a robotics research group around that time, a little later, 2016 maybe, to 2015, to start kind of looking at how could we use deep learning and reinforcement learning to sort of improve the state of robotic research. And one of the nice things about robots is they can pool their experience. So we set up a little lab of 10 robotic arms that we called the arm farm. I wanted to call it the arm pit, but I was overruled. And then we bought a bunch of toy and tool variety packs on Amazon. And we basically gave these robots a supervised task, and it turns out to be self-supervised. You can basically tell if you've succeeded in picking something up. If your gripper closes all the way, you've probably failed. If it doesn't close all the way and you kind of roughly see anything there, you've succeeded. And so basically, these systems can just practice picking up objects. I'll just play it one more time. Oops, no, I won't. Maybe I will. And then you can pool all their sensory experience, which you've recorded, and collect it every night, retrain a better model for picking things up using a supervised machine learning, push that out to all the arms for the next day's work, next day's practice, and off you go. And so this was pretty good, and got us to about a 78% grasping success rate, which is a pretty significant improvement. And then over the next couple of years, and with more work on using sort of more sophisticated RL algorithms instead of sort of just supervised algorithms, we're now at the point where for unseen objects, we have about a 96% grasping success rate. So this is like pretty big improvement, similar to what you saw in the vision sort of improvement slope, where a third of the time you couldn't pick something up. It's very hard to actually do complicated things in the world. Whereas now you're sort of starting to be able to see grasping as like something you can pretty reliably depend on and build more complex actions out of that. And then Chelsea talked a little bit about imitation learning in robotics. We think that's a pretty important way of doing, allowing robots to acquire new skills, because there's lots and lots of sort of things you might want a robot to emulate, behaviors, videos of things. So this is one of our AI residents doing important work. They write great machine learning research papers and run experiments, but here they're collecting some training data. And on the right, what you see is a few videos of people pouring stuff from different angles. And what the system is given is a few videos of that, 10 videos of 6 seconds in length or something. And then it gets to do 15 RL-based trials with a reward function of how much stuff it gets in the cup. Basically what you see is after 15 minutes, the robot from those imitation videos plus its own 15 trials can learn to pour pretty well. Not perfectly. It's maybe 4-year-old, not 8-year-old level, but for 15 minutes of practice, not too bad. So that's kind of neat. Great. Okay. So advanced health informatics. In the AI for social good, I said, I think there's tons of stuff to do here. I'm going to skip that for this talk, and I'm going to talk about it in this talk. So for the other talk, and talk about it in this talk. So I think one of the real potentials here is, can we use machine learning to bring expert care that everyone deserves to everyone, right? That's sort of the direction we should all be thinking aspirationally. How can we make sure that the best decisions are made for every healthcare decision we're making? I'm going to walk through a few different kinds of problems we've been tackling in the healthcare space. So one is diabetic retinopathy. As an example of how can we bring this kind of expert care to many places that don't have it. And so this is one of the problems we've been working on the longest in our sort of ML for healthcare research effort, which started maybe 4 or 5 years ago. We chose diabetic retinopathy because it's the fastest growing cause of preventable blindness, and there's a huge need for screening. Basically, this is a very treatable disease if you catch it in time, but if you don't catch it, then you're going to suffer full or partial vision loss. And so screening is what prevents blindness, because if you catch it in time, then you just have the treatment and it's all good. But there's 400 million people at risk for this around the world. Basically, if you have diabetes or if you're close to having diabetes, then you should really be getting screened every year. And the screening is very specialized. A doctor can't do it. You really need an ophthalmology level of training to do this. And so in India, for example, there's a shortage of 127,000 or so eye doctors, and as a result, 45% of patients lose some vision before they're diagnosed. And this is completely tragic because it's completely treatable, 99% effective treatment kind of thing. And how can we address that? So Turns out like it's a computer vision problem, largely, and the same model that can tell you that's a cat also can, with the right training data, tell you, that's severe diabetic retinopathy or that's a healthy eye. And so what you can do is basically adapt an off-the-shelf computer vision model used for general classification. This is the Inception V4 model, which is what they started with. Get a bunch of retinal images, get them labeled by ophthalmologists into these 5 categories, 1, 2, 3, 4, 5, which is how these images are graded, and then train the model on that data set. So what could go wrong, right? Well, one thing is you need high-quality labels. And it turns out if you ask 2 ophthalmologists to grade the same image, they don't always agree. In fact, they agree only 60% of the time, which is a little, a little unfortunate. Slightly more scary, if you ask the same ophthalmologist to grade the same image a few hours later, they agree with themselves 65% of the time. But you can help avoid this issue by essentially just getting every image labeled by a lot of ophthalmologists. So if you get the images labeled by 7 ophthalmologists, then that reduces the variance a lot. If 5 of them say it's a 2 and 2 of them say it's a 3, it's probably more like a 2 than a 3. And so you can get high quality data by essentially getting lots of opinions. And then if you do that, you can train a model that is basically on par or perhaps slightly better measured by F-score than the average US board certified ophthalmologist at this task, which is great, like fantastic. This was an article published in JAMA at the end of 2016. But we'd actually like to do better, right? Because if ophthalmologists agree with each other 60% of the time, that's maybe not the gold standard we should be shooting for. Turns out there's additional specialty within ophthalmology called a retinal specialist who has additional training in retinal disease, and they generally make better consensus opinions about this. So we sort of decided to change the labeling protocol for this data set, and we essentially got the images labeled by retinal specialists rather than board-certified ophthalmologists. And we used what's called a consensus protocol, where essentially the 3 retinal specialists that we got to look at each image had to agree. So you could talk it out amongst yourselves, but like you have to come out of the room with a 2 or a 3 that you all can stick to. Turns out this is fairly common. But if you do that, then you all of a sudden have a model that is on par with retinal specialists rather than US board ophthalmologists. And that's sort of the gold standard of care. That's what you'd want. And now you can run that model on a GPU on a desktop, do 100 images a second or something. So this is pretty amazing. And then you want to be able to then take that and deploy it. And so for the last couple of years, we've been working on deployments in India and then more recently Thailand, where we're working with a couple of networks of Indian eye hospitals, the Aravind and Sankara eye hospitals. And we've sort of done clinical trials with them. We've then gone through the clinical trial process. They showed that this was basically effective. And we now are deployed in those hospitals and are treating real patients. We've also, we're doing similar deployments in one district in Thailand with the intention to sort of scale that up. So, this is super important. It's like great to publish papers, but it's also really important to end up with the real world impact for these kinds of things because there are lots of people who benefit. The other kind of interesting thing is you can sort of, turns out machine learning models can see things that even trained specialists can't. So this is a bit of a tale of scientific discovery. So we had someone new join the diabetic retinopathy machine learning team, and Lily Peng, who leads that team, was trying to figure out a starter project for them so they could figure out how all the sort of software tools that the team uses work. So she said, why don't you go try to predict biological sex from these images? Because we have some images where we know the self-reported gender, I guess, of the eye owner. And ophthalmologists don't know how to do this. So the AUC really should be no better than flipping a coin. So 0.5 is kind of what she was expecting. And so the person went off and they like fiddled with a bunch of stuff and they said, oh, great, I've got it running and my AUC is 0.7. And she said, oh, no, that can't be right. Like maybe you're like testing on the training data or something. And so they went off and like, why don't you go double check for everything? So they went off and they fiddled with some more stuff and they said, I've double checked everything and now my AUC is 0.85. And so it turns out that that got people excited in the team and they like started looking at what else can you predict from these retinal images that maybe we had no idea you could predict. Turns out a bunch of different things. And you can predict a whole bunch of things that are all correlated with cardiovascular risk. And you can combine them together to make an assessment of your cardiovascular risk that is similar in accuracy to a more invasive test, like a blood draw. So basically now we have a new sort of biomarker, a new signal that we can collect, get interesting information from that even ophthalmologists who've been, that whole field has been studying eyes for a while, didn't know existed. It's pretty amazing, right? I suspect in the near future it will be fairly routine to take a retinal image when you go to the doctor, right? That's not what happens today. You only get it when you go to the ophthalmologist or the eye doctor. But a whole sequence of eye images may tell us even more. Explainability is really, really an important topic, especially in these kinds of medical-related domains where you are working with a specialist to help offer kind of an opinion, and the specialist kind of also has an opinion. You want to be able to show them, like, why is the model making this kind of prediction? Patient needs new heart, right? That's not quite as convincing as, patient needs heart replacement because of this, and this, and this, that you can then interact with the specialist and they can say, oh yeah, that makes a lot of sense, or no, that doesn't make sense. And so, if you tell a clinician, an ophthalmologist, this patient has moderate diabetic retinopathy, that's not quite as convincing as if you say this patient has moderate diabetic retinopathy, here are the parts of the eye that I'm concerned about that are making me think it's a moderate diabetic retinopathy. And you can basically use techniques for visualizing sort of the internal state of neural nets and all the way back to the input data to basically improve the interpretability of these kinds of models. So it works for kind of retinal images. We've also had some good luck with using attention-based things for medical records and medical notes so that we can show people this phrase in a medical note is sort of really an important phrase for making this kind of prediction. Okay, radiology and lung cancer screening is another modality. This paper was published in Nature Medicine last year, and it's about CT scans, which are sort of not the traditional X-ray machine you think of from when your childhood, which gives you a single X-ray image. A CT scan actually gives you kind of a whole volume of X-rays. So you get basically a stack of two-dimensional X-rays, about 400 of them, and you need to sort of be looking for whatever it is you're imaging in that sort of literal haystack of X-rays. And in particular, the problem we decided to look at was, could we use machine learning to improve lung cancer CT screening? Lung cancer is super bad if you, in general, but especially your survival rate goes way down if you don't detect it early. And so people who are diagnosed in the early stages of lung cancer are about 5 times more likely to have a high 5-year survival rate. But the screening is really hard because you have this stack of 400 X-rays and you're like looking in there for the tiniest sign of an early tumor. And the early cancer, the early signs are really subtle, and so false positives and false negatives are both a problem. And the model that they developed basically has a complete, handles the complete 3D volume, basically with 3D convolutions. And the key points are basically after they did this work, they were able to show that it basically outperforms radiologists at this task for both early stage, middle stage, and late stage lung cancer in detection. And when you have just one CT scan, when you have a CT scan taken 6 months ago and then another CT scan, several months apart, the radiologist actually did better and the model was basically on par in that case. But when you have just one CT scan, it was actually quite a bit better. So let's look at what this looks like. So this is what a radiologist is looking at, looking for tumor, right? So they have a UI where they can manipulate up and down in this stack of X-rays, and they're really just looking for the tiniest thing that could be an early sign of cancer. And this is a patient where the initial radiologist missed the early tumor. When it grew, so a year later, that it was more detectable, and so they found it then. But that's not a great outcome, because you'd rather have found it the year earlier. And so the model essentially takes the entire stack of scans, feeds it into these neural nets, sort of 2 stacks of them, one of which is trying to predict malignant lesions, and one of which is trying to predict is the whole screen not showing any cancer. And so the initial scan, turns out this system does detect that, even when it's smaller, which is nice. Okay, pathology is another thing where we're seeing similar results. You know, the medical imaging ones are sort of like, oh yeah, that's now obvious that this would make sense. Pathology is, you know, pretty interesting. It's used for breast cancer screening, and one of the big there are 2 big problems, right? Like underdiagnosis is a problem where you miss an early cancer, but overdiagnosis is also bad, because then you go in and you have a more severe, you know, you have treatment for someone who doesn't actually have early stage cancer. And so it turns out you can train a machine learning model, convolutional neural net, to do this task on relatively limited amounts of data. So actually this data set was like hundreds of images annotated by pathologists at the pixel level to say this is tumor, this is tumor, this is not. So it's actually quite a lot of rich information rather than just like a whole slide label that says cancer. It turns out with that rich information, you only need a couple hundred of these images to achieve an algorithm that gets like an AUC of significantly better than a pathologist given unlimited time. And if you look at a pathologist in the time constraints that they normally experience in the clinic, it's way, way better. So one of the things we've been working on is a sort of a prototype of a microscope that can actually do this in real time on the microscope itself. So it sort of uses a mirror to get the view of what the pathologist is looking at, runs it through a GPU card to like actually augment it, and then feeds it back in with a mirror so that you can overlay these annotations in real time as the person is moving the stage around and zooming in and out. Another area of medical care that's not imaging based is what kind of information exists in medical records that could be used to make predictions and improve care. And so could we basically use all the data in medical records, in de-identified medical records? We don't actually even need, on the training data, need to know the identity of the patient. Could we actually use this to predict you know, the future? So if you imagine sequence-to-sequence models for translation, you know, that takes a sequence and predicts another sequence. So if instead you view the training problem as, let's take the first part of a medical record ordered in time and try to predict the second part of it. That's essentially trying to do the task that doctors are always trying to do, which is, how can I predict the future for this patient? What's going to happen to them? What kind of treatments should I consider? It also can be used for hypothesizing. If I treat them this way, does that change the future in interesting ways versus treating them this other way? So like a key difference is that a lot of clinical models that are used today to make predictions of various kinds often use a handful of handcrafted features and are plugged into a formula, and you get a prediction out of that kind of formula, like will this patient come back to the hospital in 30 days if I, you know, discharge them today, or lots of other kinds of tasks like that. That's really pretty limiting in terms of the power of those models. And so if you look at using all the data present in the medical record for some of these tasks, it turns out you can do a lot better. And so this is a paper that was published in Nature Digital Medicine, which is a newish journal in 2018. Basically, what we want to show is that using all the data actually is better than using just a handful of variables for different clinical tasks. And also that we can use deep learning models for these trained directly on the raw medical record sequence to do interesting things. So FHIR is an open standard for healthcare data interchange. The details aren't that important, but it sort of has events and lots of different attributes of events, and you can line them all up in a timeline. So we think of timelines, and so there's like different kinds of medical events, like you got a lab test, and then like 9 hours and 15 minutes later, the lab test results came back, and like this level was this, and that level was that. That's essentially the kind of data that's encoded in medical records. You put them all on a timeline, and for different kinds of events, you have different kinds of additional information. And then you use a essential sequence model to predict lots of different things about this. So for example, you can predict the length of stay for a patient who's just showing up in the hospital. This can help with hospital operations. How long am I going to need a bed for this person? Do they need a special kind of nurse practitioner? Will they be readmitted? What is the total medical expense that this person's likely to incur? Are they likely to develop diabetes in the next 12 months? Can we get them some treatment for, some coaching to improve their diet? What will that do to their risk of diabetes? That sounds good, but it's only going to be useful if it actually works. We tried several different model architectures. I will say, I think the biggest improvement here is just from using all the data that existed in the medical record, not so much from the exact characteristics of models. We got modest improvements over simpler methods when the simpler methods were given all the data. But there was some gain. And I think, with healthcare, improvements in accuracy are never to be sneezed at, even if they're modest. But really, you get a huge jump from using all the data, and then you get an additional modest jump from using a neural net for these tasks. And I think partly that's because the events in the medical record are already fairly high level, fairly hand engineered, rather than sort of very raw forms of data, like every reading from every machine you were hooked up to. So it does work, which is good. It turns out you get pretty big improvements over the kind of existing clinical models of like just a handful of variables that people are using and predicting for these kinds of things. And you can predict things like, what diagnosis makes sense for this patient, which is a very hard thing because there's like 14,000 different diagnoses you might consider. I think this is pretty interesting. If you think about medical records, there's actually a huge amount of doctor wisdom and decision-making encoded in those medical records across a large healthcare system or a large country. The hope would be you can get that information to all the doctors who are making decisions through the use of sort of an augmented set of tools that help doctors make decisions. So this is an example of visualization of these models, and in particular, because we used an attention-based model, a model with attention, we can use the attention to actually show what parts of the patient medical record is the model looking at when it's making a prediction. And so in this case, this was a model, a patient where this model predicted a very high risk of patient mortality, but the existing clinical model predicted a fairly low risk of patient mortality, the one with the 27 variables or whatever. And it turns out the thing the sort of more sophisticated model that was looking at all the data was focusing on was this one obscure phrase in a medical note, the R lung plurix tract. So I'm not a clinician, but it turns out if you're a clinician, this makes total sense because this is a particular kind of catheter that you use only on terminal patients that have a particular kind of cancer. And so the fact that this patient already had a R lung plurix in their medical note is sort of not a great sign for their mortality. But it shows that the model can be interpretable in interesting and important ways. And we're doing a bunch of other things. So Turns out you can use computer vision models on retinal images to help predict your eye prescription for glasses. We can help predict foodborne outbreaks, which restaurants are likely to have foodborne outbreaks based on a bunch of interesting analysis of geospatial data. We can try to essentially create drafts of medical notes based on conversations between doctors and patients, so that a lot of in the US at least, a lot of the clinician burden is like dealing with the medical record system and entering notes and so on. And that's not really what doctors love and enjoy. They really enjoy interacting with patients, not like spending 3 hours after work typing up medical notes for the right billing codes to make sense. Turns out you can use speech recognition and transcription and segmentation of speakers to actually get a transcript. And then the more difficult machine learning problem there is, how do you go from a transcript of like a 10-minute conversation to the salient few things that a doctor would actually put in a medical note. But with summarization improving, that we can at least give some serviceable rough draft of things you might think about putting in a note. I think I'll skip most of these, but there's a bunch of other interesting work in the field of machine learning for healthcare, I would say. It's likely to be a really important area. Engineer better medicines was one of the grand challenge problems. And actually, a lot of the grand challenge problems kind of relate to understanding properties of chemicals and materials. One problem that actually one of our residents a few years ago, in collaboration with a bunch of researchers, took on was, how can we predict properties of molecules? And it turns out, if you're a quantum chemist, the traditional way you do this is you have some molecule you're interested in, and you want to know, does this thing bind to that thing, or in what way, or is it toxic? What are its quantum properties? Then the way you do this is you set up your molecule configuration, and then you run a density functional theory simulator, which is like a traditional high-performance computing style simulation, and after an hour, you get your answer, which is great. But that's kind of slow, because what you really care about is maybe 100 million molecules or something. So it turns out this is a pattern that is repeated in many different scientific and engineering domains. You can use a simulator that you have that tells you something interesting as a training device for a neural net. And so you can essentially run a bunch of examples that you care about through the simulator, get the inputs and the outputs, and then try to learn essentially the entire simulator with a neural net based on just the input-output examples you care about. It turns out for this particular problem, this works. We've also seen this work in earthquake simulation, for example. I was just chatting with a student here who's getting it to work on sort of black hole simulation things and seeing similar sort of impressive speed-ups. And the really nice thing is now you have a tool that does roughly the same thing, but basically, in this case, it was 300,000 times faster. And so if your tools speed up that much, you just do a very different kind of science, right? You're like, oh, well, I'm going to make coffee. Let me screen 100 million molecules while I go do that and then see what it says with my coffee. Whereas you would never think about doing that if you were using the much slower thing. So I think this is a trend that's also going to play out in many different scientific domains. Reverse engineer the brain was another one of these grand challenges. And it turns out machine learning is useful for that. Who knew? We actually know relatively little about the brain, including we don't even know how the brain is connected to, all the neurons in the brain are connected. And so there's a whole subfield of neuroscience called connectomics, which is trying to essentially just determine what is the static structure and connectivity in real brain tissue for a variety of different organisms. Eventually, you'd like to learn that for humans, but we're not at the scale where we can learn that. So essentially, you start with brain, you slice it very thinly, and then you do electron imaging, electron microscopy imaging of these very thin slices. And then at the end, you now have a giant stack of slices of brain tissue. The unfortunate thing is the blade you use to slice it is actually way thicker than each slice you get. So you've sort of destroyed a fair amount of the brain tissue in slicing it up. And so now you have this kind of giant three-dimensional puzzle of like this whole stack of brain tissue, and which sort of thing that looks like a neuron sort of body here is connected to the corresponding thing in the slice below and the slice above. And what you'd ultimately like to do is reconstruct the entire connectivity of all the neurons in that sort of volume of brain tissue. Or if you're a computer scientist, you might like an adjacency matrix. And we've been collaborating with a bunch of external institutions on this problem for a while. And the research team working on this has made a lot of great progress. And one of the ways they measure their progress is what is the expected run length if you start to follow a neuron's axon or dendrite? How much accumulated axon or dendritic tissue can you follow before you make a mistake? And so if that's low, like that's terrible because you don't actually get the real connectivity. But they've been making pretty significant improvements, and it's important to note that's a log-based 10 scale on the y-axis there. So it's like improved by a factor of 1,000 or so in the year or so that they've been working on this. So one of the big jumps there in accuracy, the second big jump, was from the development of a technique called flood-filling neural nets. And the essential idea here is that you use not just the static image to make a prediction, but you use the static image plus the whole sequence of predictions you've made so far to help predict the next thing you're going to, both where and what you're going to predict for the next thing. So you can sort of see that this system sort of bounces along a region where it's fairly confident and fills stuff in, and then it becomes less confident about that, and then it kind of jumps over to another part and starts filling in there, and then maybe we'll jump back. And so this is it working in 2 dimensions. In 3 dimensions, it's kind of even cooler. And so you can see it kind of follows one dendritic branch for a little while, and then it kind of jumps back to another one where it's now more confident and follows that. And so it now can recreate these beautiful pictures of neurons, which is kind of neat. And more recently, we released a sort of full fly brain reconstruction, plus some nice visualization tools. If you're super into fly brains, this is the tool for you. It's pretty neat. This is sort of the major structures that show up as you sort of start to trace through the fly brain connectivity data. Great. OK, so you've heard a lot about NLP this week, I gather. And obviously, NLP is super important. It's great for translation. It's better for understanding, does this query match this document? There's all kinds of uses for better understanding of text in the world. It's great for the summarization problem I mentioned in medical transcripts. And there's been a lot of recent encouraging improvements, starting with the sequence-to-sequence work that Oriel was involved in, and recurrent neural nets of various kinds, LSTMs before that. But really, there's been some great leaps forward, which is kind of, the transformer-based model that I think you heard about from Joe is like a really great example of something where you can all of a sudden, instead of having the sequential dependence on the processing you're doing, you can essentially process a whole bunch of data in parallel. And that makes things much more computationally efficient. And then use self-attention to kind of pay attention to the parts of it that are important for your next prediction. And it was, as a result of that, they were able to get big improvements over sort of mostly recurrent-based models. So they got both higher accuracy, but importantly, with 10x to 100x less compute than was needed for the other approaches, right? And so that's a really great algorithmic improvement that leads to then you can use the compute you would have spent on like using more data or doing other interesting things. And so this was a team of Google researchers and a couple of interns that came up with this in 2017. And then in 2018, another team of Google researchers sort of said, hey, this looks great. We think we can improve on that by using it as a building block for a more interesting model that instead of only looking in the past in sequences, looks kind of at the entire context, forward and backward, to make predictions about sort of language. And that has been like a pretty remarkable improvement in a lot of ways for a lot of different language problems. And the key thing that's really neat here is it's completely, the pre-training is basically self-supervised. So we have lots and lots of text in the world, and we can just drop some amount of the text, drop 15% of the words. And the interesting thing, if I flip back and forth, this is actually pretty hard for people, right? And you can see why this is an effective training mechanism to help you really force you to use context to predict stuff about what possible words could go in that blank, right? So pick a blank there, and remember what it is, and then that's really hard. Obama was blank in 1961, so I don't know what blank is, but then I can see that he also spent 1 year raised, so it's probably talking about childhood. So maybe born might make sense, but that was pretty hard. But that's okay. Neural nets are pretty good at this. And we'll just give them lots of data, force them to do this task over and over and over on lots of unique data, and they will get better and better at this. And so the task, obviously, is to predict what words are missing in those blanks. And the BERT model is essentially a really nice way of wiring up a bunch of transformer models to do this task. And the other important observation is this pre-training of the model on lots of unsupervised text, self-supervised text, then allows you to fine-tune the model on individual language tasks where maybe you only have 1,000 examples of the actual task you care about. Maybe it's like predicting, is this restaurant review positive or negative, or is this talking about dessert, or whatever. And that has been like pretty revolutionary in lots of ways for basically making many more language tasks much more accessible, because now you just need a little bit of labeled training data to do each individual language task, because you've pre-trained on so much data. This is a table from when that paper came out. Obviously, there have been significant improvements since then, but I think this is pretty nice work. Okay, engineer the tools of scientific discovery was another one of these grand challenge things. And it's kind of like the vaguest of all of them, right? I think they were like, oh, we've got 13. 14 would be a better number, and this one's nice and vague, so let's throw it in there. But it's clear that if machine learning is going to be an important thing about what we do in the world, it'd be nice to have a common set of tools that we can use collectively to work on machine learning problems. And I think, when we first decided to work on TensorFlow, I made the decision that we should open source it as well, so that not just internal Google users would use this tool, but lots of other people around the world would be able to hopefully work with us to improve the set of software, but also use it for interesting things that Google would never get to or never do in all kinds of interesting ways. And so it's had a good adoption curve if you look and measure it by GitHub stars, which is one measure of interest, compared to a bunch of other sort of open source machine learning packages. And I think one interesting thing about TensorFlow is it's trying to appeal to a really broad set of constituencies in machine learning. So it's trying to appeal to researchers who have one set of needs and desires, but also to people who are actually machine learning engineers and practitioners and trying to deploy these systems in real products, both running in large data centers or running in sort of mobile applications. We want to be able to target a wide variety of different computing devices and run on, all kinds of operating systems. So the surface area that we're tackling with TensorFlow is pretty large, which sometimes means it's not necessarily the best tool for any particular constituency, but it does have this really broad ecosystem, and it's really a really nice system for taking starting with a research idea, going from a research idea to something you can deploy in all kinds of different ways in the world. And we have, a pretty big community. I'm really proud of the fact that we have almost 2,000 contributors, probably over 2,000 now, of which a third of them are from Google. So the rest are sort of this outside community of, people in other companies, students working to improve the system. And people have done interesting things with it that we would never have anticipated. So in the Netherlands, there's a company that builds fitness sensors for cows. Because if you have a lot of cows, it's apparently hard to keep track of how well they're all feeling. And so it turns out, you want to know cow number 14 is happy and healthy. You can get the sensor data, analyze it with TensorFlow, or they analyze it with TensorFlow, and we'll tell you cow number 14 is great. 17 is not feeling so well today, though. If only they had names. It's so impersonal. Another research group, there was a collaboration between Penn State University and the International Institute of Tropical Agriculture in Tanzania, developed this on-device machine learning model for detecting cassava diseases. So it's not just AI for human healthcare, but plants as well, is really being transformed by the fact that computer vision now works. And so this team basically built an app where you can take a picture of a leaf that's not looking so healthy, and they can tell you, yes, it's diseased and it has this disease, and this is the way you treat it. And this is a really good example of where machine learning wants to run in all kinds of, basically everywhere in the world, including in the middle of a cassava field in Tanzania with no network connectivity. So you have to be able to run a lot of these machine learning models in sort of really computationally challenging environments, but that's super important that we be able to do that. Okay, another thing we've been focusing a lot on in our research agenda is, at Google, is how do we automate more of the machine learning process? Essentially, how can we learn to solve machine learning problems rather than sort of having human machine learning experts solve every new problem? And the current way we solve a machine learning problem typically is we have some data, or maybe we have an idea of a problem we'd like to solve. We collect the data for it. We have some computational devices, a bunch of GPU cards, or maybe TPUs or whatever, and we have a machine learning expert sit down, run a bunch of experiments, look at the results, like figure out what the next set of experiments make sense to run, do that again, repeat, essentially, and hopefully, if all goes well, you get a great solution from that approach. But the question is, can we make that much more automated? Can we remove a lot of the human ingenuity or sort of human in-the-loop experiment running that happens during the machine learning modeling process? And if we could, that would be amazing. And the reason is there's millions of organizations in the world that actually have machine learning problems. They just don't realize it yet, right? And even if they did, they generally don't have the people on staff to solve those machine learning problems. So the lower we can make the barrier to entry to actually being able to take an idea for a machine learning problem you might want to solve and actually solving it, the less sort of specialized expertise and training you need in machine learning, the better that'll be. And so AutoML and all these kinds of next set of things I'm going to talk about are how can we make that process of developing sort of robust solutions for a machine learning problem more automated. And so the first bit of work that we explored in this area was this work by Barrett Zoff and Kwok Lee. Barrett was one of our first AI resident classes. Was basically, one of the decisions a machine learning expert makes is what model architecture to use, and that's a whole bunch of individual sub-decisions. Should I use a 6-layer model or a 17-layer model? Should the filters at layer 8 be 5x5 or 3x3? Should I have skip connections or not? And so it turns out you can have a model generating model that can describe a model architecture. Initially, it starts out generating random architectures. But you can have that model generating model sample from the distribution of models and generate 10 models. And then you can train each of the models it generates on the problem you actually care about and see how well it works. And using the loss or the accuracy of those generated models, you can use that as a reinforcement learning signal for the model generating model. So if you do that and you repeat it a lot, run this loop a lot of times, then it turns out the model starts to produce more and more accurate models for the problems that it cares about, that you care about. And it cares about it because you told it to care about it. And it produces models that might look a little strange, right? Like a human would probably not sit down and wire up a architecture that way. But it's reminiscent of things that from human intuition we know are effective, things like skip connections and ResNet. These are sort of allowing input data to flow much more directly to the output by following these other alternative paths that skip a bunch of connections. Skip connections and ResNet are sort of the same intuition. And the sort of RL algorithm developed this intuition sort of on its own. And it works, which is nice. So if you look at this graph, which is a bit complicated, let me explain it a bit. So on the x-axis is computational cost of doing an inference for one image in a model, right? And the y-axis is ImageNet top one accuracy. And so the black dots, the dotted black line there, is the Pareto frontier of a bunch of human sort of machine learning expert, computer vision expert produced models that have come out in the last 4 or 5 years. Things that have sort of significantly advanced the state of the art in computer vision, things like ResNet, Inception, lots of things like that. And so what you see is that the Pareto frontier there, you generally get more accurate models as you spend more computation, right? So more accuracy, more computation gets you more accuracy. But what you also see is that the AutoML work from 2017 that developed both NASNet and AmoebaNet with these automated search methods actually outperforms sort of the whole set of world computer vision and ML teams doing hand engineering of computer vision models. And then if you fast forward a year, it outperforms it more. And just last week, which I didn't insert in a slide, there's another paper that it pushes it up further. So like this is an example where automated experimentation has been hugely effective because the system can run 20,000 experiments, and it's impossible for a human to run 20,000 experiments. And it's true in lots of other sort of modalities and problems you might care about. So object detection, for example, the ML expert sort of best human engineered models are at the bottom there. Similarly, the x-axis here is inference time, which is kind of a correlate of computational cost. Language translation, you can take the basic building blocks of a transformer and the system can learn a more interesting assembly of those basic building blocks that improves on that. Video classification, similar story. You can basically learn a better way to combine video information. Sometimes you care about both accuracy and inference time, inference cost, and so you can actually combine in a multi-objective reward function both the accuracy and the computational cost, and you can decide how you want to trade those off. So it might be that you need a model that runs in no more than 7 milliseconds. If it's 7.1 milliseconds, it's no good to you. Or maybe you have a 7 millisecond threshold, but you're okay with it sometimes running 8 or 9 milliseconds. You can decide how to combine those, and then the system can develop model architectures, actually measure the inference time on a, in this case, we cared about mobile phone latency. So we actually built we have a little data center for testing of Android. You can run experiments on that and see what the actual inference latency is on the phone, and combine that with the training accuracy objective. And so we actually use that approach with Waymo in some of their perception models, and basically showed that you could get significantly better latency for the same quality, or get better quality for the same latency, or any trade-off in between. ENAS is a kind of interesting approach where we want to make the search process much more efficient. So one of the problems with the sort of neural architecture search approach is that each time you start a new experiment, you start with completely random parameters. And that seems a little unfortunate because like wrapping another outer loop around your ML training process is never that great for computational efficiency. So ENAS is this idea where we're actually simultaneously going to search lots of architectures by picking a path through an architecture, through a collection of components to be an architecture. And then we're going to train that path for a little while. But then we're going to pick a different path, but we're going to keep the parameters that we've learned so far. And so now we're going to sort of simultaneously explore a whole bunch of potential architectures and sort of be able to make the search process much more efficient. And we've turned these into a suite of different products so that commercial customers who have interesting ML problems but don't really have the ML expertise on staff can then use these for like vision, language, translation. We actually now have one for tabular data, which a lot of sort of small businesses have. They want to predict, which customers are going to spend a lot of money with me next month or whatever. I think I'm going to mostly skip these, but this is a pretty active area of research for us. Yeah. Okay. So let me switch gears a bit and talk about computing hardware. A lot of these techniques really thrive when you can bring more computation to the problem because you can then train a larger model on more data, and generally that's a good thing in deep learning. And you can also try more experiments more quickly. There are many, many reasons why we want more computational capabilities than we have today. And so deep learning really has two nice properties that are pretty amazing relative to general purpose computing. So one is reduced precision, even to the level of like 1 decimal digit, is perfectly fine with all these models. So all the kinds of stuff I've talked about so far, most of the stuff you've heard about this week, you don't need sort of floating point or double precision level floating point accuracy. And that's pretty important. We can actually make much more efficient use of computing resources if we can build reduced precision systems. And the other thing is they're all these computations are sort of different ways of stitching together a relatively small handful of specific operations. Essentially, matrix multiplies, vector dot products, other linear algebra kinds of operations. So if we can build computers that do nothing but reduce precision linear algebra, but do it really well, that enables us to have a level of specialization that will let us get big performance improvements over other things that were not as specifically designed to do just these things, like CPUs or GPUs. So the TPU, Tensor Processing Unit, is kind of the first, TPU v1 here, is the first system we built in this space. And it was really designed to target neural net inference. When you already have a trained model, you just want to deploy it and run it on lots and lots of examples for, say, a high throughput service, like many of the Google services. It's basically a single chip on a single PCI card that you can plug into a machine. And this has been really, really effective for a lot of our inference needs because it suddenly means we have something that's like 50 times as efficient as running inference on a CPU. And we use it on all of the search queries that we do. We use it for machine translation, for speech recognition, many different things. Our DeepMind colleagues, when they played their AlphaGo match against Lee Sedol in Korea, that was what Lee Sedol was competing against, was 2 racks of TPU cards. We've commemorated this by sticking a little Go board on the side of it. These were the 2 racks. And then it's also important to think about inference at the really small scale. I mentioned the example of wanting to run on a phone in a cassava field. We'll be able to do even more in those environments if phones and other sort of really low power constrained environments can have really high power inference, high performance inference solutions. So edge TPUs are something we've been working on for a while. There's 2 of them on the penny, US penny there, so they're pretty small. And they essentially give you like 4 teraops of integer 8 level performance in a really nice small power envelope There's actually one that you can plug into an existing USB port and just uses the power from the USB port to get pretty high throughput inference. Okay, so inference is great, but really to get to that point, you have to have trained a model, and training is like often where you really care a lot about throughput and time to result. And it's the harder computer architecture problem. So this is why we started with inference. And the reason is that inference, you can usually figure out how to squeeze a model that you want to serve on a chip. And then the inference solution is you build a chip, and then if you need more inference capacity, you have a lot of these cards or a lot of these systems, but they don't interact, right? So it's completely data parallel. But training is more complicated because your model is continuously updating, and you need to sort of have more than just a chip worth of compute. Because if you had a chip worth of compute that could solve the problem you cared about, I guarantee that the next thing you'd say is, well, actually, I'd like to train a bigger model on more data. At which point, you now have to worry about how do I build a bigger system than just a chip. So you have to think about how do you get a lot of chips to cooperate in a larger scale computing system in order to train a model. And so one of the things that's really important, remember I mentioned that reduced precision. For training, for inference, we found that we can actually quantize models down to int8 or even below int4 level precision, so 4-bit or 8-bit inference integers. For training, what we found most effective is floating point still, unfortunately. I wish we could train in 4-bit integers, but we don't know how. But we don't need the full precision of 32-bit floating point representations. And the reason that's important is most of the cost in multiplying two floating point numbers, say, is in dealing with the manticibits, right? So you're essentially multiplying the manticibits of a floating point representation. And in IEEE 32-bit floating point, that's 23 bits of mantissa. With carry and overflow, that's 24 by 24 full adders you need to build a circuit to multiply a IEEE floating point number. And IEEE has a standard now for 16-bit floating point, where they essentially drop some of the mantissa bits and some of the exponent bits. And that gets you down to 11 mantissa bits, or 10 mantissa bits, and you use, then you need 121 full adders. Now, it turns out for machine learning, what you care about is dynamic range, but not precision. So you'd actually rather lose more of your mantissa bits and keep all your exponent bits. But that's not the choice IEEE made for the FP16 format. So we actually came up with a format several years ago called bfloat16, which essentially is the IEEE 32-bit format minus 16 mantissa bits, because that was easy. It turns out we were using this to encode and decode floating point numbers across the network, and we wanted to reduce the network communication, so we would just send 2 of every 4 bytes and then go on to the next 2 bytes. And that worked pretty well. But it turns out it actually turns out to be a great representation for machine learning training because it has this kind of dynamic range that the 32-bit floating point representations have, but you can build a multiplier circuit with just 64 full adders because it has only 7 mantissa bits. Okay. Anyway, an aside. So we started to build systems for that were good for both training and inference. And so this is the 2nd generation TPU that essentially this is one device with 4 chips on it, and it's the chips are connected together. And if you look inside one of these chips, you see that the computer architecture is actually really, really simple. It's basically a giant matrix multiply unit. Every cycle, it can do multiply 228 by 228 matrices together. It has some scalar and vector units for things that are not matrix multiplies, but why would you want that? But sometimes you need them. And then it has high bandwidth DRAM memory, HBM. And it has 2 cores on the chip, and then the memory on the side, which is way simpler than a traditional CPU, right? Traditional CPU has all kinds of things like branch predictors and caches and TLBs and all kinds of crazy things. This is why specialization makes sense, because now you can devote all of your chip area to matrix multiply units, or a lot of it. This 3rd generation TPU, well, what has gone on? I don't know what happened. I fiddled with the slide formatting and copied from another deck. Anyway, there's a 3rd generation one that looks like the 2nd generation one, except it adds water. Water cooling, so the water kind of flows directly to the surface of the chip, gets heated up, goes to the next chip, gets a little hotter, goes to the next chip, gets even hotter, goes to the next chip, gets even hotter, and then gets pumped away. And these systems are designed to be connected together into larger configurations called pods. And so this is the 3rd generation pod configuration, which is essentially 8 racks of these systems, 1,024 of those chips, connected together in a 32 by 32 grid. So think of it as a 2D mesh with then wraparound links on both ends. These systems are quite high performance. In particular, the networking between the chips is quite high bandwidth, which is really good for giving you roughly linear scaling on a lot of different kinds of machine learning problems, both data parallel and model parallel problems. And so, for example, you can train a ResNet image model in less than 2 minutes from scratch on this system, which is roughly 1 epoch per second. Or you can train a pretty large BERT model in roughly an hour. And we have a bunch of different sort of open sourced models of kind of a wide variety of vintage that you can pick and use for training models for problems you care about. And so we're pretty excited about TPUs. We use them for nearly all of our machine learning needs these days internally. And think you should too. They're available through our cloud. And one of the things we think is really important is that we know lots of people in the community tend to sometimes not have access to the computational resources that they want to try out their ideas. And so one of the programs we've created is TensorFlow Research Cloud, which is roughly 1,000 of those cloud TPU devices, the 4-chip devices, available for free for researchers who are really committed to both, doing something interesting with them and then publishing about that, releasing to the world some results of that research, publishing a paper, ideally open sourcing code related to it. And we're excited to see what researchers outside of Google will do with more computation. We think that's a really empowering thing. And so one of the things I'd like to do for Khipu attendees is give you access to more compute. So operators are standing by. No, I'm just kidding. There's a form you can fill out. I will say they're like a different model than a GPU. They're not a drop-in replacement for a GPU, but if you can figure out how to express your problem in a way that makes TPUs work, they're pretty great. Like a lot of the alpha star work was developed on TPUs. Lots of the stuff that I've talked about has used TPUs. Anyway, so we think this is going to help researchers try out new things that they wouldn't otherwise. So, okay, I'd like to finish with what's wrong with how we do ML. So I sort of mentioned this already a little bit. We start with an ML expert, and then they have an idea of a model architecture. They initialize it with a random floating point number generator. We add some data. We run a bunch of training iterations. The numbers get a little bit better. And then we have a solution, right? So with AutoML, we start with data. We don't start with the ML expert anymore. We add compute. We start with random floating point numbers still. And then we get to a solution. And that seems like a problem, right? Like for every machine learning problem that we look at, we collect a data set, we initialize our knowledge of the world with a random number generator, and then we say, great, now I'm going to run a bunch of training loop iterations and see what happens. And that's pretty lame. That would be like forgetting all of your schooling for every new thing you want to do. So that means also that new problems need huge amounts of data because you're trying to learn everything about the world from nothing in order to solve this problem, and significant compute because you're trying to learn everything about the world from nothing. And so sometimes we've seen already early glimpses that transfer learning, when you have a large pre-trained BERT model, for example, can make a huge difference. You can fine-tune a BERT model with relatively little compute, and it can tackle a new language task with relatively little data. We've seen similar things in fine-tuning of image models. But that's still something that is pretty manual and kind of ad hoc. And it's done at the scale of like, sometimes when you do multitask training, it's at the level of like, let's train these 5 tasks together because they all seem kind of the same or similar. Okay, so how can we do better? So I think we want bigger models than what we have today, but we want them to be sparsely activated, right? Like most of the models we use today, you put in some data and you activate all the floating point multiplies the model could ever do for every example. And that seems kind of unrealistic. So we want to have this large capacity, but activate only a tiny portion of it. So per example routing is something I'm pretty excited about. I think, the ability to have a model where you can learn different pieces of the model that are good at different things, and then learn to send a particular example or maybe a particular task in the direction of the expert, that part of the model that is good at that thing, and the rest of the model stays silent and doesn't do any work, is something pretty promising. So this was something we worked on a few years ago to essentially have what's called a sparsely gated mixture of experts layer. So the pink things there are traditional LSTM layers, and then the sparsely gated mixture of experts layer is inserted between a couple of these layers. And it has a few things in it. So one, it has a bunch of experts, with each expert being like a little miniature neural network. And it has lots of experts, 2,000 experts or something. And it has this little green thing which learns to activate the experts that are appropriate. So every example during training, it picks a couple of experts, say, and sends them to those experts. And then through the magic of backprop, you can actually look at the gradients and decide which expert was better suited for this example. And then you can update your routing function in the green box to say, well, I should send this kind of thing more to expert 2 and not expert 73. And then you sort of repeat that process throughout the training process. So you're simultaneously training the experts and training the routing function. And it turns out this works pretty well and turns out to be more computationally efficient, which I think is an important thing to note. That's the main point of this. So in particular, the baseline here was the bottom row, which is the Google machine translation system without a mixture of experts layer. And then the top row is if we add mixture of experts to it. And what you see is that we got an improvement of 1 blue point, which is pretty significant improvement in accuracy. We got a drop in computation per word. And the reason we got that is we're able to shrink the size of the pink layers. So the computation that we activate on every example can be made smaller and can be compensated for by the huge capacity we have in these experts. And so overall, we spend about half the inference cost per word. We have about 1/10 the training cost. Unfortunately, these were done on slightly different GPU generations, but think roughly number of GPU days. So it was like 64 GPU days versus 6 times 96 GPU days. Roughly 1/10, maybe a little at an 1/8 or something. And then the total parameters in the model is the main thing that is way bigger. So I think this kind of thing is pretty promising. And so if we look at stitching some of the ideas together from the talk, what do we want? We want this large model, but sparsely activated. I think we want a single model that does many things, right? So we can leverage our expertise in doing other things, in doing a new thing. I think we want to think of neural architecture search as maybe more like something like we want to, if you squint at neural architecture search and say, look at it more from the ENAS-like perspective, how can we find good paths through a large model that already exists that get us into a good state for a new problem we care about? Right. So I have a cartoon diagram that kind of illustrates this. So imagine we have a model like this that already solves a bunch of tasks. And in particular, it's made up of a bunch of different components where each one is some piece of an ML model with some state and operations. And then a new task comes along, right? So now imagine we run some RL-based pathway search system to look at what paths get us into a good state for this new model, for this new task. And let's say we found that one. Hey, that one works really well because it leverages the representations that these other components have learned and seems to be effective for this new task. We can even say, we really care about this task. Let's make it more accurate. So let's add a new component and start letting this task use it for its purposes. And so now we have a bit more compute capacity, and now maybe that path, that task becomes more accurate. But more importantly, we've also got now a new component that can be used for other tasks, right? And there's a whole bunch of interesting ML research issues and systems issues in such a system. Like how do we avoid forgetting how to do one thing when we learn to do another? I think you can solve that with some shared components and some components that are dedicated to particular tasks or particular subtasks, sets of tasks. And maybe each component is running its own little miniature architecture search inside it so that it's adapting to the kind of data it's being sent and simultaneously improving itself. Okay, finally, I'd like to close with thoughtful use of AI in society. I touched on this a little bit in the AI for Social Good panel, so I won't dwell on it too much. But I think it's really important that we, as researchers, have opinions about how our research should be used and what kinds of problems we want to focus on. And one of the things I'm proud of is that last year, Google, we've been thinking about this as we started to use more machine learning in many of our products over the last few years. And we sort of decided to be a bit more concrete about how we thought about our principles in using machine learning. And so we, after a lot of thought, came up with this set of principles, and there's a lot of sort of text behind them on the website that we think are pretty important properties to be thinking about as you're using machine learning for all kinds of different things in the world, or thinking about using machine learning. And I think it's important to note that a lot of these areas are active research areas in the field of machine learning. So reducing bias and unfairness in machine learning models, is stuff you can look at from an algorithmic perspective and develop better and better algorithms. And people are doing that. I think what we try to do is apply the best known techniques when we think about using machine learning in our products, but also advance the state of the art in a lot of these areas, as is a lot of the people in the rest of the community. And just to give you a sample of some of the work we're doing along these kind of areas that touch on the AI principles of fairness, bias, ML privacy, ML safety. We have about 75 research papers in the last year and a half or so that really touch on different areas there. So it's definitely a fast-moving field, a set of fields. But I think it's really important that we all get this right. And with that, I want to conclude, and I hope I've convinced you, maybe you're already convinced since you came to Khipu, that machine learning is really going to be changing not just computer science or ML, but has these broader applications in the world. And we should all work to make those applications really, the beneficial ones really happen, and that we can make the world better. Cool.
Excellent. Thank you so much for this great talk, Jeff. And we will open for a few questions from the public. In the back, there is one all the way to the back, all the way, last row. There is one.
Hi, is it? Okay. Thank you so much for the talk. I wanted to ask about the AutoML. It sounds like it's going to leave us out of work, so I'm pretty sure it is not. So, do you have any intuitions, or have you seen which type of task are the ones where it fails, where you really need human intuition to develop a machine learning solution?
Yeah, so at first, it's not going to put us out of work. And I think it actually plays really well with the strengths and weaknesses of human machine learning researchers. So the reason is the system is very good at running automated experiments in some search space that a AutoML researcher defines, right? And actually creating that search space is a bit of an art and is actually a human ingenuity kind of thing that is pretty hard. You know, make it 10 to the 10th, it won't find anything good. Make it 10 to the 80th, it won't either because it's too big. 10 to the 30th is a great sweet spot. But the reason I think it's going to be amazing, both for practitioners but also for machine learning researchers, is imagine an AutoML system that has a whole bunch of problems that are solved with it, and you come up with a new idea in machine learning research, right? The way you currently evaluate your new idea is you say, okay, I have a few problems. I'm going to plug my thing in and like see how it does compared to the baseline, and hopefully I get state of the art and I can publish on this problem. Or no, it's not that bad. But imagine a different world where you wake up, you come up with your idea, and when you go to bed, you put it into an AutoML system that is used for 1,000 tasks. And in the morning, you get a report that says, well, your new thing wasn't that useful in 93% of them, but in these 72 tasks, it was used, and this is the way the system decided to use it, right? I think you would actually develop really good intuitions and have a really good sense of how well your new idea is sort of used and useful in solving machine learning problems with a system like that. So I think it's going to be great. And I will also point out crafting the search space is a bit of an art. So.
Okay.
We have one here in the front.
Hello. Hey. So here.
Oh, sorry.
So wonderful talk. Thanks again, Jeff, for making it to Uruguay and for supporting Khipu. So my question is about quantum computing. So there's been great advances in terms of quantum computing in the last years, and Google is doing great efforts on that field. So what's your take on quantum computing? What do you think that could be the opportunities, and what are the goals of Google with these technologies?
Yeah, so I didn't talk at all about our quantum computing research effort, which is a pretty significant effort. You know, we have probably 50 or 60 people working on this in both the quantum computing hardware side of things and also what are the programming models that make sense for quantum computers, which is not an obvious thing. I think the technology is still really nascent, right? Like we just in the last couple of weeks ago, were on the cover of Nature for the quantum supremacy result, which maybe if I interpret that result for you, it will show you where we are. So what that showed is for the first time, a quantum computer could solve a problem, a particularly carefully chosen problem, that no classical computer could solve in reasonable amount of time, like in 1,000 years, 10,000 years, something like that. And the problem that was chosen was simulate a quantum circuit, which you might imagine a quantum computer might be good at. But I do think it's an indication, and the reason you're limited to the problems today is basically there's a limit to the number of qubits, the sort of basic building blocks in the quantum computer you can have, but also because they're not 100% fidelity qubits, they have errors that magnify the number of steps you run. So basically you're limited right now to running roughly 20 steps on a 56 qubit computer. So if you squint at your problem and it fits in that sort of 56 qubit, 20 steps kind of thing. That's great, but very few problems do at the moment. There is a potential big breakthrough in quantum computing, which is to create error-corrected qubits, that would then be 100% accurate, and you could run arbitrary length computations. I think that will be a really, really big improvement. That's likely projected to be 10-ish years out, because you need roughly 1,000 qubits to build one error-corrected qubit, and we're not near there. But at the same time, in the intervening years, we're going to have a set of problems that are applicable for quantum computers, and as they improve in size and the number of steps you can run before we get to error-corrected computing, quantum computing, then certain kinds of material simulations that actually take advantage of the quantum properties of quantum computers could be really interesting. I think like factoring of prime numbers is still pretty cryptologically interesting size. Prime numbers is still pretty far off, given what we have. But it's important to pay attention if you're a cryptographer, I think. So that's sort of where we are. I think it's still pretty far off from people who do general computing having to care. But on the other hand, quantum computers are also good at optimization, and optimization is a lot of what ML is used for, or is at the heart of a lot of ML algorithms. So it could be useful there. It's probably not yet.
Okay, I think there is a question there.
Hello? Yeah.
Hello.
I love that idea of having a single big model that can solve all the tasks. We want 1,000 different tasks. I think it's elegant and beautiful. It just feels that fewer and fewer people or research groups would be able to be competitive in terms of doing research in that kind of scenario where we need 1,000 different data sets and a cloud of TPUs to run it every time we want to change something. Mm-hmm. So I don't know if there's a question here. It's just feels like the contribution of Google to the world would have to be, okay, here are the TPUs for free, and here are the 1,000 data sets so that everybody else can keep competing, because otherwise it's just competing in the healthy sense, right? We all contribute to science, and not just the ones that have the infrastructure.
Right. So, so first, we realized that a lot of organizations could use more computation. That's why we're doing things like making TensorFlow Research Cloud available for people. I think in my career, I've seen several subfields of computer science go through a bit of transition. So, for example, the field of distributed computing was in the early 90s and mid-90s mostly an academic thing, right? Academic labs could have a rack of 20 machines and do like really interesting distributed systems work at the cutting edge of scale that people cared about. And then things like search engines and online email hosting services and other things made it so commercial entities started to have clusters of 1,000 computers or 10,000 computers. And that meant that some of the distributed systems problems that are involved in operating those things started to be encountered first in industry and not in academia. Now, that didn't mean that distributed systems work stopped in academia, right? It just meant that certain kinds of problems made more sense to do in industry, but there's still a lot of other kinds of distributed systems research that goes on in academia and other environments that don't have thousands of computers, but are still looking at interesting issues in distributed computing. And I think machine learning has been going through a similar transition over the last 5 or 7 years or so, where suddenly it's so commercially interesting that a lot of commercial entities now have a lot of interesting data sets, a lot of computational capability. And that doesn't mean that machine learning research in academia isn't a thing. It means that the problems you pick should probably be ones that are where you can demonstrate an interesting new idea and show that it's good, but not necessarily at the largest scale possible. I think we still pay tremendous attention to interesting new ideas in the community. I think we need to get away as a community from saying every new paper has to be a state-of-the-art on the biggest data set possible, right? That's not healthy or useful. What we actually want is new, unique ideas that show early promise on something that is not necessarily at the scale of 1,000 tasks with, simultaneous things. So I think, it's really important to sort of balance that and realize that we as a community should help shape what is valued and useful. I do realize there are certain problems that are easier to tackle at large institutions with large compute. Such a system, I think, might actually be interesting as a collaborative exercise that everyone in the world works on to improve. But who knows? It's still a very early research project at the moment.
Okay, great. In the interest of time, this is going to be our last question, but I think Jeff is going to be attending the event tonight. So
yes, because I want dinner.
Yes, because he's hungry, so you can ask him things there. But we have a last question here from Alejandro.
Very quickly, Jeff, how profound do you see, given all these technologies related to AI, how profound do you think the transformation of society will be in, say, pick your timeline, but 10, 15, 30 years?
I mean, I'm not very good at predicting the future. I think one good thing to do is to look back, say, 10 years ago and look at what the transformation was from the sort of, probably the steepest part of the deep learning sort of curve and a wave of sort of the second wave of work there. And basically we've gone from no computer vision to now computer vision working. That has dramatic implications that I think, we're starting to see real world, we have seen a lot of real world demonstrations of impact there, but there's so many applications of the world where the fact that you can now see with a computer haven't been taken advantage of. And so I think the next 10 years for sure, you'll see pretty dramatic changes across a large number of different sort of industries and problems and things like that. I think it's hard to say what will happen in 20 years. I think, there's clearly going to be, a lot of deployment of new technologies like autonomous vehicles are probably likely to be fairly deployed in 10 years. Probably not replacing every car on the road, but, I could imagine, some significant fraction of cars on the road being autonomous. And that would actually change how you think about building cities and infrastructure and all kinds of things like that. So that'll start to happen in like a decade, I would guess. I mean, that kind of significant impact in infrastructure and that kind of thing.
Okay.
It sounds like a great dinner topic.
Yes. Stay here after you thank Jeff, because Fefu has a few words to say. But let's thank Jeff once more for this
Thank
great
you.
talk.